Have you ever stood outside and just known the weather was about to change? Not because the weather app buzzed in your pocket, but because of a strange stillness in the air, a funny feeling in your head, a deep instinct that the day was about to break. What if that's not just a feeling? What if it's data that our bodies are able to understand? Your body is a sophisticated weather station, constantly collecting information. For thousands of years, our very survival depended on reading these signs. Today, we're going to reactivate that ancient software. We are going on a deep journey to learn the language of the sky, the wind, and our own senses, to read the weather with no app required. To do that, we first need to understand the stage on which this all plays out. Our atmosphere. We think of it as just air, but it's a vast dynamic ocean of gases, and we live at the very bottom of it. This ocean is surprisingly thin, but it's all that separates us from the void of space. If the Earth were the size of an apple, the atmosphere would be no thicker than its skin. And what is that skin made of? Mostly nitrogen, about 78%. It's a stable, largely non-reactive gas that serves as a sort of neutral backdrop. About 21% is the oxygen we cherish, the fuel for our bodies. The remaining 1% is a mix of other things, but a crucial part of that 1% is water vapor. That airborne moisture is the ink with which the weather writes its stories. This atmospheric ocean isn't uniform, it's layered. The layer we live in, the one that touches the ground and extends up about 10 to 15 kilometers, is called the troposphere. The name comes from the Greek word tropos, meaning to turn or to change. And that's exactly what it does. It's in a constant state of turmoil. It's the weather layer. It contains nearly all of the atmosphere's water vapor, and it's heated from the bottom up by the sun-warmed earth, causing constant convection, warm air rising, cool air sinking. This is the churning that creates our weather. Above the troposphere is a stable, stratified layer called the stratosphere, which contains our precious ozone layer. The boundary between them, the tropopause, acts like a lid, trapping most weather phenomena below it. So when we look up at the clouds, even the very highest ones, we are looking at features contained entirely within this thin, life-giving troposphere. The engine for all of this is the sun, because the Earth is a sphere, that energy isn't distributed evenly. This temperature differential between the hot tropics and the cold poles is the ultimate driver of everything we call weather. The atmosphere is in a constant global battle to find balance, moving heat towards the poles. This movement creates our global wind patterns and the massive air masses that clash to form storms. Now, this daily, weekly, and seasonal churn of events is what we call weather. It's the snapshot. It's the rainstorm tomorrow, the heat wave next week, the cold snap next month. But if you zoom out, a larger pattern emerges. That long-term pattern, the statistical summary of weather in a location over decades, is what we call climate. Think of it this way. Weather is the specific outfit you choose to wear today. Climate is your entire wardrobe. It's the collection of clothes you own because you know, based on past experience, what the seasons will generally be like. Here in Brisbane, my wardrobe is full of shorts and t-shirts, but very few heavy winter coats. That's because our subtropical climate dictates our long-term expectations. Scientists use systems like the Köppen classification to map these wardrobes across the globe. It divides the world into zones: tropical, arid, temperate, continental, polar, based on temperature and precipitation patterns. Brisbane sits comfortably in the humid subtropical zone. This tells us to expect hot, humid summers with significant rainfall, often from thunderstorms, and mild, drier winters. Understanding your local climate is the first step in understanding if the weather you're seeing is normal or something unusual. It's the baseline against which all daily observations are measured. With that baseline established, we can begin to look for the daily signs of change, and the most beautiful signs are often painted with light. The sky is a canvas for breathtaking optical phenomena, created by the interplay of sunlight with the water droplets and ice crystals in the atmosphere. The most famous, of course, is the rainbow. It's a phenomenon so common we forget how magical it is. It's not an object. It's an optical illusion that is unique to every observer. It's formed by sunlight entering a raindrop, refracting or bending, as it enters the denser medium of water, reflecting off the back of the raindrop, and then refracting again as it exits. The initial refraction separates the white sunlight into its constituent colors, just like a prism. Because of the specific geometry of this reflection and refraction, we see the arc of colors at a precise angle of 42 degrees from the point opposite the sun. This is why you can only see a rainbow when the sun is behind you and the rain is in front of you. Sometimes you might see a fainter, larger secondary bow outside the primary one. This is caused by light that reflects twice inside the raindrops before exiting. This double reflection reverses the order of the colors, which is why the secondary bow always runs from violet to red, the opposite of the primary. But water isn't the only artist. Ice crystals high in the atmosphere create their own brand of magic. When thin cirrus clouds are present, these tiny hexagonal ice crystals act like millions of miniature lenses. When they are shaped like plates, they can create bright spots on either side of the sun, known as sundogs or parhelia. When they are shaped like columns, they can create luminous halos around the sun or moon, or pillars of light that seem to extend up from a sunrise or sunset. And then there is the most fleeting and sought after of all optical phenomena, the green flash. For just a second or two, as the very last sliver of the sun disappears below a sharp, clear horizon, it can flash a brilliant emerald green. This happens because, as the sun's light travels through the dense atmosphere at the horizon, it's bent or refracted. The shorter wavelength colors, like blue and green, are bent more than the longer wavelength reds and oranges. This separates the color slightly, like a weak prism. For a brief moment, the red and yellow parts of the sun have already set, but the green and blue, which is usually scattered away, is still visible just above the horizon. It's a perfect alignment of physics that lasts but a moment. These beautiful displays of light are part of a larger story, one that has been woven into human culture for eons through folklore. The most famous of these is likely the saying, "Red sky at night, sailor's delight. Red sky in morning, sailor's warning." This isn't just a rhyme. It's a remarkably accurate forecast for the mid-latitudes, where weather systems predominantly move from west to east. Let's break it down. For a red sky at sunset, the sun in the west is shining its light through a thick slice of the Earth's atmosphere. This long journey scatters away most of the blue and green light, leaving only the longer wavelength reds and oranges. If that red light can reach you and illuminate the clouds above you, it means the air to your west, the direction from which weather is coming, is clear and free of storm clouds. Clear skies to the west means a high-pressure system is likely overhead or on its way, bringing fair weather for the sailors next day. Conversely, a red sky in the morning means the clear sky is to your east, where the sun is rising. The red light is illuminating the undersides of a bank of clouds to your west, the direction the weather is coming from. A bank of clouds in the west is the leading edge of a weather system, likely a low-pressure system bringing rain or wind, hence the sailor's warning. It's a simple, elegant observation of light and atmospheric conditions. But our ancestors didn't just look up, they listened and felt. Let's explore the deep connection our own bodies have with the changing atmosphere. Let's start with what you can smell. That distinct, earthy smell before rain, petrichor, is caused by the compound geosmin being released from dry soil by rising humidity. The sharp, clean smell of ozone can be carried down by a thunderstorm's downdrafts. Our sense of hearing also provides clues. A temperature inversion where warm air traps cool air below it can make distant sounds seem remarkably clear, a classic sign of a stable air mass that often precedes rain. Then there are the feelings within our bodies. The drop in atmospheric pressure before a storm can cause our body's tissues to swell slightly, potentially causing aches in joints or old scars. And most critically, hair on our arms standing on end is a direct physical reaction to the immense electrical field of a nearby thunderhead, a final urgent warning to seek shelter from a potential lightning strike. If our own bodies are this attuned, the animals we share this planet with are even more sophisticated. The eerie quiet before a storm is an entire ecosystem reacting. Frogs, with their permeable skin, are living humidity detectors, often croaking more as the air moistens. Bees, sensitive to electrostatic charges, return to their hives. And some animals have what feels like a superpower, the ability to hear infrasound. These low-frequency sounds generated by large storms travel for hundreds of kilometers. A study of golden-winged warblers showed them evacuating their breeding grounds a full day before a massive tornado system arrived, likely hearing its distant low-frequency rumble. Even the much-debated topic of animals predicting earthquakes has a plausible scientific basis. It's likely not prediction, but early detection. An earthquake's initial non-destructive P waves travel faster than the destructive S waves. Sensitive animals likely feel this first tremor seconds or minutes before humans feel the main shaking, giving them a head start. But the atmosphere's display of light and the subtle shifts felt by living things are not always so serene. Sometimes the same ingredients, heat and water, combine not to paint the sky, but to unleash incredible power. Let's delve into the anatomy of the most extreme storms on Earth. We begin with a tropical cyclone known as a hurricane in the Atlantic and a typhoon in the Pacific. This is not just a storm, it's a heat engine of monstrous proportions. It begins as a simple disturbance, a tropical wave over warm ocean waters typically above 26.5 degrees Celsius. If the conditions are right, low wind shear and plenty of moisture, this disturbance can begin to organize. The Coriolis effect, caused by the Earth's rotation, gives it its initial spin. As moist air is drawn in, it rises and condenses, releasing enormous amounts of latent heat. This heat warms the core of the storm, lowering the pressure and causing the winds to strengthen, drawing in more moist air in a powerful feedback loop. A mature cyclone is a masterpiece of terrifying structure. At its center is the eye, an area of calm, sinking air and often clear skies. Surrounding it is the eye wall, a ring of the most violent thunderstorms with the fastest wind speeds and heaviest rain. The storm is rated on the Saffir-Simpson scale from Category 1 to 5 based on wind speed. But often, the most destructive element is the storm surge, a mound of water pushed ashore by the powerful winds, causing catastrophic coastal flooding. Here in Queensland, the memory of cyclones like Yasi or Debbie serves as a powerful reminder of their force. While cyclones are vast, organized systems, another type of storm packs its power into a much smaller, more violent package: the tornado. The most powerful tornadoes are born from a specific type of thunderstorm called a supercell. A supercell is a thunderstorm with a deep, persistently rotating updraft called a mesocyclone. This rotation is created by wind shear, winds blowing at different speeds or from different directions at different altitudes, which creates a horizontal rolling motion in the atmosphere. A strong updraft can then tilt this horizontal roll vertically, forming the mesocyclone. If this rotation tightens and intensifies, it can lower from the base of the storm as a wall cloud, and from there, a tornado can descend. Their destructive power is measured on the Enhanced Fujita EF scale, based on the damage they cause. For millennia, this deep sensory connection and fear of these storms was the state of the art. Humanity's understanding of the weather was qualitative, a story told in clouds and feelings. But then, during a great awakening of curiosity in Europe, the human approach began to change. We began to quantify. This instrument revolution began in the 17th century with a student of Galileo named Evangelista Torricelli. He created the first barometer, proving that we live at the bottom of a sea of air and that its weight changes. Around the same time, the thermometer allowed us to measure temperature, the hygrometer to measure humidity, and the anemometer to measure wind speed. The next great leap required connection. The invention of the telegraph in the 19th century allowed for the creation of the first weather maps. For the first time, we could see the vast, swirling structures of high and low pressure systems moving across continents, but we were still blind to what was happening above us. That changed in the 20th century with weather balloons and radio sondes, which sent back data from the upper troposphere, revealing the jet streams that steer our weather. The final revolution was seeing it all from above. On April 1st, 1960, NASA launched TIROS-1, the first successful weather satellite. Humanity saw for the first time the swirling, organized beauty of a cyclone from space. Today, a constellation of satellites are our ultimate sky people, watching the globe 24 hours a day. So, let's synthesize it all. You wake up and see high, wispy cirrus clouds. You know now, like the Latkuxta of the Chugach, that they are the first sign of a distant system. But you also know this is because a warm front is pushing moisture to the freezing altitudes of the tropopause. You see a sundog and understand the physics of the ice crystals creating it. You notice the local birds are quiet and the pine cone on your deck is closed. Your body and the local ecosystem are confirming the change in humidity and pressure. This deep, multi-layered understanding is a powerful thing. The instruments and satellites have given us an incredible ability to see the big picture, but they haven't invalidated the ancient knowledge. They have, in many ways, explained the science behind it. The goal isn't to choose one over the other, but to integrate them. The world is in a constant conversation, telling a profound scientific story. So the next time you step outside, just take a moment, look up, listen, feel the air on your skin. Watch the other creatures you share this world with. See what story the sky is telling you. You might be surprised at how much you already know.